Good night, Poly students, and how are you? Blah, blah, blah. I don't like that one at all.
You're on.
Am I? Okay. Hello, crazy kids. Same hat, same shirt, same books behind me. And if you're watching this evening, you're probably a senior approaching your fourth quarter at the Polytechnic School. And you're probably thinking one of two things. I'm hoping you're thinking, thank you, college counselors, for making me take this class. It's not that bad at all. In fact, I've really enjoyed it. Although they were right, that guy is a bit of a character, that Mr. Fletcher. Or perhaps you're thinking something else. Something along the lines of, wow, Polytechnic School really does a great job with this interdisciplinary learning stuff. Where else would you be able to study honors physics and have your own personal experience of all 9 circles of Dante's Hell? But I digress. Today what we're going to learn is a little bit about taking a veloraptor, Dielectric, that's what I mean. Not a dialect, not a diuretic, but a dielectric, and placing it between the boundaries? Plates of a capacitor. Enjoy.
Okay.
Good evening, Polytechnic School, and welcome to another scintillating video from Honors Physics. Same hat, same shirt, same books behind me. In tonight's episode, we're going to look at taking a dielectric and placing it between the boundary, the plates
of a capacitor.
Of a capacitor. I think we better go with the first one.
Okay, that's fine. So as you can see, the wonders of modern makeup and hair extensions have rendered me considerably more attractive than I normally appear during class. But enough about me. Here is our three-dimensional capacitor. Here we have one plate. Here we have a second plate. Here we have the area in between the plates. And as was promised in the preamble, we are going to put a dielectric in between the plates and see what happens. So here's a cutaway view of the capacitor. Here are the plates. Here's the area in between. And if we charge up the plates, this side positive, this side negative, we're going to have an electric field in the region between the plates, set up like so. So again, what happens when we take a dielectric and pull it into the region between the plates? As the dielectric descends, notice what it does to the electric field lines. So what's happening? So the charge carriers in the plate set up this electric field, as we've said, and it in turn generates a van der Waals effect along the face of the insulator. If you remember back when we talked about van der Waals effects, what's happening is that the atoms along the face of the insulator, their electrons are trying to get as far away from the electrons in the capacitor plate here as they can. And in doing so, it ends up making it look like the face of the insulator itself is electrically positive. By the same token, on this side, where the capacitor plate is positive, the electrons in the atoms of the insulator are trying to get as close to the positive charge as possible, and the consequence is it makes the face of the insulator look electrically negative. So what you end up with is a face along this side that looks electrically negative and a face along this side that looks electrically positive. That induced charge in the dielectric sets up an electric field that goes from the apparent positive face to the apparent negative face. It's a weak field. It's induced and it's not very strong, but it's still there. That weak induced electric field that was generated in the dielectric adds negatively to the electric field that was generated due to the fact that there's charge on the capacitor plates, and you end up with a net electric field between the capacitor plates that's less than you would have had if the dielectric hadn't been in between. With the diminishing of the net electric field, the voltage across the plates drops, and you get an interesting thing happening to the definition of the capacitance. Definition of the capacitance says that you want to take a look at the charge on one of the plates and divide it by the amount of voltage that you have across the plates. The amount of charge on one of the plates hasn't changed, but the voltage across the plates has dropped with the insertion of the dielectric, which means this ratio has become larger. In other words, putting a dielectric between the plates of a capacitor increases the capacitance. Looking at things a little differently, by dropping the voltage across the plates, it means you can now put still more charge onto the plates before the electric field between the plates hits the breakdown level. Which is to say, you now are in a situation in which you can put more charge per volt onto the capacitor. Additionally, if you take the ratio of the capacitance of the capacitor without the dielectric, with just air in between the plates, and divide it by the capacitance with the dielectric in between, you will come up with a constant. That constant is called the dielectric constant. You can see that if air is the dielectric, then with and without are going to be the same, and the dielectric constant is going to be 1. So the dielectric constant for air is 1. You can also see that without the dielectric is going to be a number smaller than with the dielectric, which means the dielectric constants are always going to be greater than 1 for insulating materials other than air. And the last observation having to do with this is that this is actually the form you usually see that relationship in. Usually you're given the capacitance without the dielectric, you're given the dielectric constant, and you're asked to figure out what the capacitance is with the dielectric. So bottom line, there are 3 ways that you can increase the capacitance of a capacitor. You can increase the plate area. That allows you to put more charge on the plates per unit volt. You can bring the plates closer together, which would also allow you to force more charge on per unit volt. Or you could put a dielectric between the plates, which would additionally allow you to put more charge on per unit volt. And that's about it.